Okay, so last lecture we introduced the op-amp and we looked at a number of sample circuits. Today we're actually going to look at a couple more circuits and then we're going to actually see what happens when we basically deviate from ideality. So when we don't have a gain that's infinite effectively and where our input resistance is basically not infinite but very large and our output resistance is not zero but very small. So that's the topic of today's lecture. We're going to actually study a circuit with non-ideality to show how the actual gain deviates from the predicted gain, assuming ideal op-amp behavior. All right, so let's look at an example. So this is another one of these two transistor problems. So this actually showed up in an exam in the past, so I would pay attention. So here what we have is we have this particular circuit where the plus terminal is grounded, so that would make us automatically know that this is 0 volts. This plus terminal is grounded, so that makes us know that this is 0 volts. So then to analyze this, what we would basically do is just do KCL here. I'm going to call this Vx, which is just a latent variable or a temporary variable. So what I'm going to get actually is that C ddt of 0 minus Vn plus 0 minus Vx divided by R have to be equals to 0. And what that means is that Vx is actually going to be equal to R times C times negative d dt of Vn. So I just factored out the negative value. Okay, so that's kind of what Vx is. We could also do KCL here, and we're going to get that uh, 0 minus Vx divided by R, right? So 0 minus Vx divided by R, that gives us a current coming out, plus 0 minus V out. And remember that we have to apply the formula for a capacitor, which is plus C d dt equals 0. And now we can actually just go ahead and move the V out to the other side and multiply by R. And so we're going to get that Vx equals, or negative Vx equals RC ddt of V out of t. And yeah, so all I did here was just move the V out to the other side and multiply both sides by R. At this point, I can back substitute my expression for Vx. And so I'm going to get basically RC ddt of Vn of t equals ddt of V outs of t. Oh yeah, and then there should be an RC here. Now, as you can see, the RCs cancel. You can cancel them for both sides of the equation. And in the end, you end up with actually that Vn of t equals V outs of t. And so you get that that's actually equal to e to the negative 0.5 t u of t volts. That's it. So you just analyze this particular circuit. At this point, we haven't learned what this u of t is. It's what's called a unit step function. It's 1 whenever time is greater than 0. But you don't even need to differentiate this equation at this point. So because the derivatives basically canceled out. So you could still solve this, presumably. Okay, so that's another example. So this is kind of an interesting one because what happens is that the gain of this circuit and this circuit is equal and opposite to each other, and so they cancel each other out, and at the end you get that the output is equal to the input. Okay, so here's another interesting one. This is a fairly complicated circuit, I would say. It's a good practice example. So one thing to note here is, of course, that VA has to be equal to VB. To analyze this circuit, we would actually have to do KVL. So we could try KVL going around this loop. And what we're going to get is basically, if we start at VA, so we have kind of VA minus, so that's the voltage here, minus I times R1. So I is the current flowing through this circuit. And then from here to here we have plus VF. And then from here to here we have minus I times R1. And that should actually be equal to VB. And then the voltage from here to here is 0, basically. Yeah, so we have, yeah, so that should actually be equal to 0. Yeah, so here should be minus VB, but then you know that BB and BA are the same, so these two go away. Okay, so at this point we have that, so you have here VA, and then you have minus VB, and at this point you have basically the voltage drop between A and B is 0, so that those two basic BA equals BB, so then that's 0, so now you're left with kind of VF equals 2I R1. Okay, so that's one equation. Additionally, you know that no current flows through here, so whatever current flows through here has to flow through here. And so you end up with basically that you have two other equations. So you have here that VA has to be equal to negative I R2, and that's equal to BB. And you also have that VB equals V out, right, plus I R2. But then you also know that VA has to be equal to BB because the two terminals are the same. And so you end up with V out equals 2I negative 2I R2. So basically I plug this in here and then I move the IR2 to the other side, and then I end up with that. Okay, so that basically means that I is equal to V out over R2 times negative 2. Wait, sorry. Over 2R2, sorry, negative 2R2. And I can just back substitute that into this expression here. And so then I get that VF equals negative uh, V out over R2 times R1. And that's it. I've just solved this circuit. Okay, in the next slide, I solved this a little bit more cleanly. So let's go through it. So like I said earlier, you can go through this loop equation. So you have a voltage drop from here to here of R1 times I. And then you have a voltage increase from here to here of VF. So I guess I started my loop here. So BF, and then I have a voltage drop from I1 times R. So that's this one. And then I have a voltage drop from BB to BA, so BA minus BB. And then I have another voltage drop from here to here, which is negative I times R1. And then just like in the previous slide, I said that, well, VA equals BV, so this is 0. So I ended up with this equation. And then I can do this nodal equation, which gives me that negative I, which is basically the current coming into here. And then that has to be equal to VB minus, so plus VB minus V out divided by R2 have to be equal to 0. And then, of course, I can solve this for I. And then this nodal equation basically tells me that, again, I, but now I is coming out, so it's positive, plus VA minus 0 over R2 has to be equal to 0. But remember that VA is equal to BB, or I can also subtract this equation from this equation. So I'm going to get minus I, BB minus VA minus V0 over R2. And then the BB minus BA cancel out. And then I end up with the same expression I ended up in the previous slide, which is V out minus 2 over R2. So there are multiple ways to get this here. So finally, I can actually plug this in. Now I can use this I and plug this in here, which is what I did right there. And now, of course, the negative 2's cancel, and then you get a ratio of R2 over R1. And then when you move VF to the other side, and then you multiply it out, you end up with this as being the gain. Okay, so this is kind of basically what as you can see from our previous lecture and this lecture, when you analyze these circuits, the two things you have to realize is that no current flows into these things, and that VA will always be, the voltages at both input terminals are the same. All right, so we've gone over a lot of examples. Now we're going to actually look at a more interesting example, which is what happens when the operational amplifier does not behave ideally. And to do that, we're going to look at this simple circuit, which we've already studied ad infinitum, which is this inverting amplifier configuration. So in this particular case, we know that this voltage will be equal to this voltage, which is 0. And then by applying KCL, we have 0 minus Vs divided by 1K plus 0 minus V2 divided by 5K. So that gives us this equation. And then as you recollect, we move 1 to the other side, and then we actually can calculate the gain to be negative R2 over R1. And in this case, that is negative 5 volts per volt. And if we make R2 50K, then it would be 50 volts per volt, and so on. Okay, so that's fine. This is when we assume that, of course, the gain is infinite. The input impedance Rin is equal to infinite, and R out equals 0. So let's see when we deviate from this. So to study that, what we have to go is we have to go back to our equivalent circuit. So here's kind of our amplifier equivalent circuit that we've derived for all of our amplifiers. And in this particular case, we're still assuming the output resistance RO equals 0. So we're only going to be considering the input resistance and the gain to be finite. And we're going to study what happens as the gain increases. Now note that the symbol for this particular voltage controlled source is reversed. That's because the gain of the ideal operational amplifier is actually negative infinity. So we flip the polarity to note that actually we have a negative gain. Okay, so let's analyze this new circuit that we have here. So how do we analyze it? Well, now when we apply KCL, we're going to have a current this way, a current this way, and a current this way. And the value for those currents would be, we have, so we're going to have that this is grounded. And so what we will actually have is, we will have that VA minus Vs over R1 plus VA minus 0 divided by R2 plus VA minus, oh sorry, not R2, RI. RI, V out, or V2 divided by R2. So that's actually our new KCL. So now we have 3 terms. And so we can actually combine the common to both terms, which would be the VA terms and the V2 terms. And so we're going to get here actually that, hold on, so we're going to have V2 over R2 equals 1 over R1 plus 1 over RI plus 1 over R2 VA minus Vs over R1. Cool. Now we need an additional equation, as you all can tell here, because we have 3 unknowns and we only have 1 equation. The second equation we know is that actually V2 is equal to negative K times V1, VI, right? So this is VI. But VI is actually equal to VA minus 0. And so we actually know what so this thing here is actually VI or V2 over K. Okay, so what we're going to have here is actually, let me just plug. So this is actually equal to negative K VA, or another way to write this is that VA equals V2 over K negative. All right, so I'm going to go ahead and plug this in, all in. So I'm going to get actually that V2 equals so V2 equals 1 over R1 plus 1 over R2 RI plus 1 over R2 VA and then we need to divide by k, and then there's a negative sign. Oh, and then we need to multiply everything by R2. So R2, 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 and then minus Vs over R1. Now, one thing to note here, if k is infinite, then automatically that second term is 0, and you can already see that we get the gain of our the previous circuit that we just described. Now, so if k, as long as k is large, this term will be very small, basically, which is what we would expect. If k is large, that means that this thing behaves approximately as ideal, and this should be actually V2, not VA. Okay, so here I actually derived it a little bit more cleanly. So this is the original equation I had for my KCL applied by evaluating the 3 currents. And then this is that equation that I got for what V2 in terms of VA. And then I was able to come up with this equation in the previous slide. Now here I did the algebra slightly different so that I actually would end up with a nicer expression. So what I actually did here is I replaced all of the, just like I did before, I replaced wherever I had a VA with V2 over K. So here I have 1 over KR1, and they have 1 plus 1 over KR R2, and then I have 1 over KRI. So basically, if you look here, there's a 1 over KR1, and then there's a 1 over KR2. But then there's also a V2 here, so it's 1 plus 1 over K. And so there's still a minus sign here, basically. And then this third term becomes 1 over KRI V2. So then you just move the Vs to the other side, and so now, and you combine all of the like terms associated with V2, and you end up with this complicated expression. But this is just all of these in parallel. And then those end up being multiplied by Vs, and so you end up that the gain V2 over Vs is actually equal to R2, KR2, KR1, KRI. Now, just as before, remember, if I plug in infinite for K, then R2 is in parallel with a bunch of infinite resistances, so that just gives you R2 over R1. So you could see how this is already kind of getting you the correct gain expression. So now what I'm going to do is I'm going to plug in 1 kilo ohm for R2 and 1 kilo ohm for, 5 kilo ohms for R2 and 1 kilo ohm for R1. And then I'm going to plot different values of K and see what the gain is. So that's what we have here. For this particular example, I actually chose the input resistance to be 50 kilo ohms. So the input resistance would be 50 kilo ohms. And I chose the value, and so as I vary K, if K is small, so if K is 1, you can see that our gain's pretty bad. If K is 100, we're getting closer to 5, and then by the time you're at 1,000, 10,000, it starts getting, it's basically behaving ideal. And each time we add a digit to K, we get an extra digit in how accurate our result is. So like if K is 10 to the 5, our gain is actually 4.9997. So as we can see here, our results, the bigger the K, the closer we get to our idealized behavior. And K in general, so here our gain was 5. In general, as long as K is much greater than our actual gain, which is in this case is 5, so let's say if it's 100, 10 times bigger, you're already getting pretty close. Or 20 times bigger, you're already getting pretty close. Now, let's say if we modified our circuit so that now instead of having an R2 of 5,000, we have an R2 of 50 kilo ohms, which would change it so that now our gain is actually 50. And what we will observe here is that if we change, and here now I actually make the input resistance really large so that it doesn't affect our circuit. And what you can already see here is that before, our gain was very close to 5 at 100. Now at 100, our gain is actually pretty far from 50, which would be the ideal gain. But once we are at 1,000, we notice that it behaves approximately the same. So as long as we are like a factor of, as long as our actual gain or gain of our circuit is about 20 times larger than the gain that we design our circuit to have, we're fine. So do realize that, the thing kind of behaves as infinite as long as you ask for a gain that's much smaller than the k. So if we ask for a gain of 5 and k is 1,000 or greater, we're going to get a gain of 5 or very close to 5. If we ask for a gain of 50, we need to be at least 10,000 to get something very close to 50. And I mean, if you're actually basically at 1,000, you're still going to get something close. Just like if you're at 100, you're going to get a pretty good gain, but not quite super accurate. So this ideal prediction is good as long as our gain is quite large. In this lecture, I actually did not, in this particular class, I stopped going over this, but in your lab, you will build an operational amplifier circuit. And that circuit will have a gain that approximately is equal to 10 to the fourth. So you could see that for that kind of circuit, you can get about a gain of 50 and still assume ideality. If you go to a gain of 500, you're going to start kind of very clearly seeing the deviations from ideality. And in real life, you will always have what's called the common mode gain, which is related to the average of the input and output voltage. This is really bad because, like I said earlier, what's common to both inputs, it's usually noise. So if there's like a truck going by as you're like one of these cyber trucks that are really heavy, as you're operating your amplifier, you're going to pick that truck in this terminal and you're likely going to pick that in this terminal. So that truck input is going to be common to both inputs, even if you're having a measurement here and somewhere other location here. And so you want your circuit to actually reject an average signal, which would correspond to kind of what's common to both of them. And but in real life, that doesn't really happen. Another common mode thing is, for example, the light bulbs. They emit a 60 hertz signal. If that's gonna be common to both terminals, and in an experiment, you're gonna see that. So actually, we were doing these experiments at one point, and like we were trying to measure some neural signals, and it was so sensitive that we had to shut down the lights, like turn off all the lights in the lab. And it would be really amusing because a student would pick up a laptop, and as they moved, you could see the laptop on the like signals. That's how sensitive these amplifiers were. And so we also had to like move all electrical equipment to the other room to do this like neurological measurement. And the culprit of all of this was this term here. And so what you typically want an amplifier to have, it's a very high common mode rejection ratio, which is the gain of the difference divided by the gain of the common mode. This is another non-ideality thing. I realized that we haven't really gone over as to how this arises phenomenologically in this class. You will see it in your lab, and it is something that you will see in data sheets. And just do realize that you want this to be as small as possible. And that's kind of how things get expensive. Okay, so that's basically non-ideality. Yeah, so that's common mode rejection ratio. So there's kind of another non-ideality thing that can happen. So if you actually buy one of these devices, an operational amplifier, so there's I think the UA474 or 71. It's like a Texas Instrument design, old. They're really cheap. They're like 7 cents. When you actually buy this, this is actually a 5 terminal device. And so the way what you actually have is kind of the minus terminal, the plus terminal, and which are the 3 terminals that we've been studying. But then there's the B plus and V minus terminal. So there's actually 5 terminals. And those 2 terminals actually correspond to, if you think of your original amplifiers designs, they all had to be DC biased by some VDD and VSS. And none of our amplifiers and none of these amplifiers can ever give you an output voltage that is not within the range of these 2 input voltages. So actually this B plus is actually your VDD and your VSS or your DC biasing circuits. And so if you ever ask for a gain that exceeds these values of the biasing circuit or VDD or VDS, what you're going to get is clipping. So just to give you an example, let's say I plug in 5 volts here and I plug in negative 5 volts here. And then my input has a 1 volt signal. And let's just assume, so in this particular case, I should get a gain of 10. So what I should actually see out of the amplifier is this. What I will actually see when I do this in a lab is this, where I get the actual gain, but then it clips. So it doesn't quite go to 10 and it doesn't quite go to negative 10. That's because you can never gain more than your DC bias points. And so that's called clipping. So that's another source of non-ideality that you could see in a lab. So we have clipping, we have the amplification of common mode, we have a finite input resistance, and then we also have effects due to finite gain of the amplifier. So those are kind of a lot of the things. And yeah, and so again, the input resistance will decrease with frequency because you have to remember that there's always going to be some kind of transistor there. And typically your input for this particular designs are connected to a gate. Well, there is a gate to source type of capacitance there. And so you are going to have, if you keep increasing the frequency, eventually you will have a resistance associated with the input. So that's kind of another source of gain. And your typical output resistance is in the order of 100 ohms for the circuit that you're going to build in your lab. Of course, there are much better operational amplifiers, but they're also expensive. And so getting a small RO, getting a high common mode rejection, getting a very high frequency for this to occur, that's going to cost a lot of money, basically, typically. And so you typically will figure out what you're trying to do, because if you're trying to do, like a voice signal, like an amplifier for a microphone, hey, audible signals do not exceed 20 kilohertz. So you could just basically say, oh, well, I don't really care about the CGS because that's going to occur at megahertz. So there's no point in buying some really expensive thing with a very high frequency breakdown because you're just not going to operate at very high frequencies. Same thing like for an audio amplifier, if you're going to connect it to a 20 ohm speaker, this is not acceptable. You're going to have to find an amplifier that has a much lower output resistance. So all of these things are things you have to keep in mind as you do engineering, that there's always going to be non-ideality, and that's mostly why we go over this lecture, that so that you understand that our models They give us a good idea of how things will behave as long as we use things correctly. But if we use things incorrectly, they're not going to behave well. And so when we look at our data sheets, we have to make sure that all of the data sheet parameters fit our application. Yeah, so that's all I have for today, and I'll see you all next time.